All right, so let's focus the first part of class on several problems about washers and discs and shells. Oh my. Now, please understand, do you guys understand what I mean when I say washers and discs aren't two different methods? They're the same method. Washers are just one big disc minus the little disc. So they call it washers, but it's the same method. Just you have to use them twice. You guys okay with that? All right, let's remember what everything is. And then I got a little handout with some extra practice stuff. So the idea behind discs is, if I have if I have to rotate some shape around something like the x-axis, right? So you don't have to ever draw any 3D. If you really draw it well, you can do it and show off. If not, maybe don't try it, like me. I rotate this. Everywhere that I rotate is going to end up being a little circle. Right? So it's actually going to be a full disc. Right? So I'm rotating this area. So when I rotate it, you can imagine the area going through space. So it's going to be a volume at the end. It's going to be this area repeated many, many times over. But if I break that area down, the whole thing with integration is I break an area down into very, very small pieces and then add all those areas up. Here I'm adding the idea of rotation, so we end up with a volume, but it actually breaks down to the same thing. Instead of rectangles, I'm now considering little disc. I'm breaking it up to a bunch of discs. So I'm going to add areas up, and the area, of course, of these circular discs are pi r squared. R is going to be related to the function, the height. Now, why do I say related to? Because if I do some off-axis rotation stuff, you have to add or subtract different amounts based on how far away that axis is. So here, in this case, if this is f of x, what would r be? What's the radius for any of these little circles? Yeah. Well, the radius would be f of x. So here's one circle. The radius is f of x. And then I just take that and rotate it through. Okay, maybe. So here I've got this, and then I just rotate that, and I end up with, of course, that disc. And if I just do that at every point, I move along the x-axis, and I do it at every little point. Move to the next one, take that disc. Move to the next one. Now it's gone down a little bit, take that disc. Now it's gone back up a little bit, take that disc. Add up all those areas, I end up with the volume that I move through. This idea actually is where, I can't remember how much I talked about this, but like the formula for the volume of a cylinder, right? Pretend like this is a can that's been through a lot of stuff. But it's just the area of a circle repeated, right? That's exactly the idea. Here it's very simple because the circle is the same through the whole region. So it's really just integrating that constant area through, right? So if I go from 0 to h, and this area is pi r squared, then it's going to end up being pi r squared h. I'm just going to add pi r squared h times. Okay, maybe. So we've seen this idea before, this idea of just stacking areas and they go through a volume. You end up with a volume at the end. All right, how are we doing so far? All right. That's the idea of it. Then you get in the weeds of the nuts and bolts. How do you apply this stuff? If I'm rotating around the x-axis, I must have dx for washers discs. Right? That's the way to keep this stuff straight. If I do shells, it's always perpendicular to that axis. So if I was rotating this stuff and I want to use shells, I would need dy here. Let me say this again. This is an important, probably the most important step because it sets up everything that comes after it. If you think I need to use washers or discs here, I'm rotating around something parallel to the x-axis, in this case, the x-axis itself, I need to have dx. Which means what's got to be true about the function? It's got to be already or easy to put in terms of x. And my limits are going to be how far I go from to on the x-axis. Do you see what I mean? It sets everything up. So that's the step a lot of people sort of gloss over and just start throwing shit in there. But this will make you look at things correctly. Can anybody tell me very quickly, how do I know this is not going to be a washer? Why is there no inner outer radius? That's what washers really have. It's got an outer big guy and then I cut the middle out. That's all a washer is. It's two discs where I subtract them. Why is this not going to be a washer?
It's just one function.
Doesn't matter.
You're rotating along a portion where the function is included. So we're not rotating along like y was negative.
Exactly. The function hugs the axis of rotation over the entire range. There's no inner part to subtract. If I rotated around y equals -2, then there would be this inner part that there's no function. I have to. That would be a washer. Then that would be the inner radius of 2. Okay, I like it. So again, if I rotate this around, it's going to be solid. There's not going to be any hollow parts. If I go around y equals -2, this whole area is going to be hollow. If I rotate this around, it's just going to end up, so like if I take this and I rotate it around, there's going to be a big hollow thing in the middle, right? So if I have this and I rotate it, it's going to have this hollow bit in the middle. This whole region is going to be hollow. This is just going to be on the outside. It's going to be this really weird kind of, maybe it's like a didgeridoo is what comes to mind. Right? They have this weird bumpy outside because it's made out of a tree, whatever the hell, and it's got the hollow inside so you can actually make air flow through, make it sound. You know? All right. Didgeridoo math, I like it. There's no inner radius to talk about. If I go around this instead, then there's an inner radius and an outer radius. The axis goes until it hits the bottom of this, and then it goes until it hits the outer part. There's an inner and an outer radius. If the function hugs the axis of rotation all the way through, there's only one disk. I don't have to do any minus. There's no washer piece to subtract out. So, for example, on the practice test, there's what I call the banana problem. If you've tried this, you know what I'm talking about. It looks roughly like this. I have a feeling not many of you tried this yet. And if I rotate this around the x-axis, this is very obviously going to be an inner radius, outer radius. This whole thing in the middle is going to be hollow. Yeah, I like it. Cool. Somebody gave me this bowl once, or it was a bowl, and then there was a hole here. And I'm like, that's not a bowl. I don't know what that, almost a neck piece if I could squeeze my head through there. I'm not sure what to do with this shit. So this would be a really crappy cup because there'd be a big empty spot in the middle. This would rotate around. It would look like this. And I guess it would just be the infinite pour cup. I mean, it depends. It's just ceremonial. I don't know. Okay. All right. So again, do you really have to understand fully what I'm saying right now? There's other ways to look at this, but to me, it makes the most sense. It's going to be just a pure disk. It's only going to need one thing in here if it hugs the axis of rotation. It's not going to have any hollow parts in the middle. Now, does this hug that axis if I go down there? Nope. Big hollow part in the middle. I've got to have an inner and an outer radius. I like it. So for around the x-axis, this would be pi times f of x squared, because it's pi r squared. If I did around y equals -2, oh yeah, then we go from, I don't know, a to b, whatever. dx, right? If I do y equals -2, then it'd be pi integral a to b f of x squared. That's the outer radius. What's the inner radius? What would that be? Just 2. So minus 2 squared. Maybe. But again, I argue that they're really the same method. Just one of them, you have to do what I call a cookie cutter problem. You have the whole dough minus the part you want to cut out, right? Chunk. Yes?
So the outer radius, would it be 2 plus the function?
Yeah, thank you. Where am I at? Yeah, here would be 2 plus this. I like that. I was so focused on getting this piece. I didn't think about that. So it would be the function height plus this 2. Good. Okay. Let me think. What else can I say about discs and washers? That's pretty good right there. All right. So, looking at the same thing, what about shells? Do the same function here. Around roughly there. About there. Now, if I were to do shells and I'm rotating around, let's see. All right. If I'm rotating on the y-axis, so the whole thing about shells is that the rectangle that you're going to rotate to make a shell is sitting on the axis perpendicular to what you're going to rotate around. So here's a representative rectangle because I'm going to rotate that around to make that chunk of the shape. And then I'm going to add the next one over, the next one over. I'm going to add those chunks together to get the whole volume. All right, so that's why the D part of this is perpendicular to the axis you are rotating around. How do I find my rectangles? How do I find them? What axis do I march down to find them? In this case, I march down the x-axis, right? So if I'm going rotating around the y, this will be integral dx. So discs, this will always match up with the axis you're rotating around. If it's the x-axis or parallel to the x-axis, it's dx. If it's the y-axis or parallel to the y-axis, dy. Washers have to, discs and washers have to do that. Shells are the other way. And if you think about it, the reason that one might not work could be that one of the main reasons is I can't solve this function for the correct letter. That's one reason to say that's why the other method exists. Because whatever this needs for dx, then the other one can do dy. Let me stop here for a second. I think I've impressed upon you at least that figuring this out is a step that you can't go past. If you can't figure out which one this is, you can't do anything else. You can guess and hope. All right, just a lot of you guys like, that gets me through, man. So over here, if I'm going around the the y-axis, how do I locate my rectangle? It's going to be whatever x value is. Do you have to add or subtract anything here? No, because I'm doing it off the y-axis. So this rectangle is x away from the axis. It's only if it's off axis when you have to adjust the radius. And in this case, we talked about this being the surface area of this cylinder that we're going to make. So if I take this and I rotate it around, I've made this cylinder, this open-centered cylinder. So the whole idea is the surface area of this is 2 pi r, and if I multiply by the thickness of course is dx. That'll give me with the little volume element. So what I really like about these two methods is this one adds up a bunch of areas and ends up with a volume. So it's sort of like the area of the floor times the height of the room is the volume of the room. So it's repeated areas. Add up all the areas of the floor, stack, 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 and you get a volume. Or I could just fill this whole thing up with cubic foot cubes. Boom, 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 and add up how many there's to take. If I add up all the little volumes, I get the entire volume. That's this method. Adds up a bunch of areas, gets a volume to go through, adds up a bunch of volumes to get the whole volume. Okay, so here, the radius is almost always just x or y. Is that you locate those rectangles along an axis. So in this case, it's just x. If I was rotating about y x equal -2, then it would be x plus 2. Very similar to this guy. H is pretty much almost always the height, the f of x. Right? If you had this problem, then the height of a rectangle would be f of x minus g of x. The top function minus, that's how tall that rectangle is. It makes too much sense to believe, that one piece, at least. So the height is going to be just how tall a representative rectangle is. So over here, why wouldn't I draw a rectangle like this? It includes too much, don't it? I just want to draw a rectangle that goes from the top to the bottom. So of course, how tall is that? Well, it's the top minus the bottom. That's how tall a damn thing is. So it's just like that section 6.1, f of x minus g of x. Okay. So in this case, it would be 2 pi. Those are constants. They can come out. The radius is x. And the height is f of x in this case. All right, so let's try some problems out. If you weren't here last time, I'm really sorry for you. I've got handouts from last time, very colorful little explanatory handouts, but I have to get them from my office. Let's try some examples, and then I'll give you this little handout to try. Let's see. Let's take one right out here. All right, let's see. X equals 2. So those first 3 lines just describe the region that we're curious about. So I want to go x equals 2, y equals 1, and y equals x cubed. I don't think they give us any more information, do they? Okay. And of course, what is x cubed doing? So it comes in like 2 goes to 8. And then of course it's back here. So let me see which. Oh, okay. So here it comes. So you see how this region, let me see, they didn't do a great job here, did they? Y equals 1, x equals 2. Ah, okay. So this is the one that's totally captured by all those walls, right? Here's one wall as the function itself. Here's another wall at x equals 2. Another wall at y equals 1. So here's the area that's captured by all 3 of those. Yeah. Screw it, Jeff, you made it worse. So y equals 1. x equals 2, and then this wall is the function itself. On the test, I'll try to be a little more explanatory, because if you start working with the wrong region or something, then you're screwed. Obviously, I would only take points off for that, and then if you did everything else right, you wouldn't lose any more points. I'm more curious about the conceptual usage than if you make one little mistake at the beginning, that kind of sucks. Try not to let that hurt you twice. But this is the region they're talking about, and they want to go about y equals -3. They're going to rotate about this line. Let's take some of this out of here so we can focus. There we go. So that's the reason I'm talking about. Going to rotate that about y equals -3. So the first thing you got to consider, okay, so now the most important thing is, how can I tell relatively easily which method to use? Right, that is the burning question. If I use, so what method do you think I should try first? Washers? Okay, now, and of course you could tell it's going to be a washer. How? Because there's a lot of empty space. Right? So I'm going around something. What's important about the fact that this, I'm rotating around this line here? How's that going to help me? What's the immediate thing it means for me? Good. I know it's going to be integral dx. There's the space in there. Which immediately means, what are the limits going to be? Yeah, what's the x doing across the region going from 1 to 2? See, people skip that step and worry about it later after they've drawn other shit on here, and then they get really confused. But my region is defined in terms of x from 1 to 2. It almost feels like cheating, but remember, everything else at right there, at 1.5, there is going to be a disk that's defined with the inner radius, of course, disk and outer radius. All the other stuff is going to be included in the work. The limits just give a shit about what this is doing. That's why that's a great first step. The immediate next step is what your limits are, so you don't convince yourself that it's more complicated. What is x doing, going from 1 to 2? Let me put my little pie out here. Now, what's my inner radius going to be? Yeah, it's constant here, right? That's what's important. It goes, you always do big minus small, so 1 minus -3, 4. If this wall was a function, it would be whatever the function is, minus -3 plus 3. Okay, I like it. So this is going to be, so the inner radius is 4. What's the outer radius going to be? Yeah, 4 plus x cubed. Well, you gotta be a little careful. Where's x cubed? Where's that height? What's x cubed? It goes from here to here, right? So if the inner radius is going to be this much, then the outer radius is going to be, let's see, so we got, this is the, like the inner radius. That's the part that's hollow. Then the outer radius is going to be, if you do 4 plus x cubed, do you see how that's going to be too tall, right? What is the, how do I want to say this? Right here, both radii should be the same. That's where they both kind of meet, right? So the inner radius is 4. If this is 4 plus x cubed, what is at 1, what's that outer radius going to be? When x is 1, what do you get for the outer radius there if I use this? 5. That's up here somewhere. All right, maybe. So remember, the function value is already the distance away from the axis. So how much are you really adding on there is going to be 3. All right, so real quick, it's because that some of the hollow part is built in between the x-axis and the base of this. So even if I was going around the x-axis, the inner radius would be 1, but the outer radius would just be x cubed, not x cubed plus 1. Maybe. This is even a better problem, I thought. Okay. So, real quick, a lot of the problems we've done, I think, before this, had a function that was hugging an axis. So if I just rotate around something that's 2 away, then the outer radius would be the function height plus the 2. This isn't hugging that. It's not going to work that easy now. You just got to stop and think, how far away from this is this? Well, it's x cubed. That's x cubed plus 3. Maybe. And see how everything I'm doing is purely 2D. I haven't had to draw any 3D to be able to set this up, thank God. All right, so now that I've got both of these, I can set this stuff up in here. So it's going to be outer radius squared minus inner radius squared. So the whole thing, pi r 0 squared, minus pi r inner squared to cut that center out, cut that cookie out.
How did you decide how far up to like make the rectangle that's in that area for the top part of the
How did I figure this out?
No, but how tall to go?
I just went to this wall here.
But for the rectangle that you drew in it.
Oh, all right. So here's the outer radius, right? Now, why did I pick right there to draw that line? Just because it's easy to see. It's not too close to either. I could have used this one instead. In fact, it's not a bad idea sometimes to do a few. Where do I always start? -3. Where do I always end up? X cubed. So now watch the way to really be careful. Take the big one minus the small one. What's x cubed minus -3? X cubed plus 3. You won't make that 4 mistake from earlier. So here, how do I do the inner radius? I started at the axis, and I went out till I hit the inner wall. How do I get the outer radius? I started at the axis to go out until I hit the outer wall. Does it matter where you do that? No. But you do a few of them just to really make your head go, oh yeah, I always go out to that wall. What's the definition of this wall? X cubed.
I'm sorry, but where did the 3 come from?
It really is because of this.
Okay, it's just that area?
That's 3 away from a main axis, yeah.
Okay.
Yep. Yeah.
So it's the 3 because it's not truly x cubed. Part of it was removed when you said it was along with the y1. So part of it was removed, so it's not the area of x cubed. So it's, you have to add, it's the 3 instead of the 4 because part of it was removed.
Yes, exactly. That's already included as a removed piece. That's another way to look at it. I like it. Okay. You guys are awesome. This does require thinking about it. And questions, if you have a question. If you feel like you have too many questions, ask now before I get too much deeper into this. How are we doing so far with everything that's happened? Trust me, if you have a question, so does everybody else. Yes?
This is washer, correct?
This will be washer, but I mean, it's important to know that so you know to look for an inner outer radius. But when you look at your axis and you start looking, it should be immediately obvious there's an inner and an outer radius. There's an inner wall and an outer wall. So if I did the same thing, real quick, if I did the same problem, but so here's 1. There's 8. So I have the same area, and I rotate it around this line. Now this has got its own issues, but then I only need a radius. If I start drawing from the axis out, I just hit the outer wall. The inner wall is on the axis. It doesn't come into play. There's no space there to consider. This is what I mean by hugging the axis of rotation. Now this is going to be a little bit weird. Let's see if you guys, how long is this? Here's the x cubed function. How long is the thing I just drew? And I can draw a few of them if I want to. How long is that line?
X cubed is 1 minus 1.
Beautiful. So my radius, my only radius in this case, will be x cubed minus 1. Because then x cubed is in relation to the x-axis. I have to subtract that 1 that I hopped over, right? I like it. Yeah, so there is some drawing, there is some thinking, there is some drawing arrows and thinking about distances. There's some of that. All right, and then this is not, now it's the easy part. All right, you just got to multiply this out. You get x is 6 plus 6x cubed plus 9 minus 16, so minus 7. And then that's easy. I mean, that's the easy part. So you get pi x7 over 7 plus 6x4 over 4 minus 7x from 1 to 2. And I mean, now I don't want to do that. Just plug a 2 in there, plug a 1 in there, subtract it, and put a pi on it. Okay. All right, let's do another one. Oh, maybe we should have done that one too. Yeah, here we go. What about y equals square root of x equals 0, y equals 2. Around the x-axis. So first just draw a sketch of this. X equals 0 is also known as the y-axis. The x-axis is y equals 0, and the y-axis is x equals 0. People always get those turned around because you don't think about what it means. So x equals 0, y-axis is one wall. Y equals 2 is another wall. And then square root of x is the other wall. So where is that going to meet that other wall there? So it meets one wall there. And of course it meets the other wall at 4, right? What's up? Sorry. When is the output 2? At 4. So it's going to... so here's one wall. Here's another wall. That's where it hits both walls, and then here's the function wee. So it should feel a little bit like the one we just did, just turned around. Which makes sense. Square root is the opposite of square. That was a cube. It's pretty close. But do you understand what I mean by, do you see the difference? It's not this is not the area. This is the area I'm going to rotate. That's the one that's captured by all of those walls. So yes, the first step is rough sketch, put the walls in. You can dot the walls all the way through and then erase the parts you don't need so your brain doesn't go all crazy, just like I'm doing. Okay. Your brain will find a way to go crazy, but you can do everything you can to prevent that from happening for a while. I'm going to go around the x-axis. So you could, let's look at both methods. Let's kind of compare both methods. Let's look at discs first. So it would actually be washers, right? You have to figure out an inner radius and outer radius. It wouldn't be horrible. It looks like the inner radius would be. What would the inner radius be? From the axis to the first wall you encounter. Yeah. And then, so that's the inner radius. And the outer radius,
2 minus square x.
don't overthink it. Not, you're thinking about the area I'm just curious about. How long is that arrow I just drew? Period.
Yeah.
2. Do you guys understand that? Where's the center of every circle going to be? The axis of rotation, right? So the radius is always going to be the distance from that to where I stop. So the inner one is when I hit the first wall, pop. And then the outer one is when I hit the next wall. How tall is that? It's the same height all the way through. That's why it's constant. Is that cool? That's why drawing a couple might be a good idea. Although this one, the inner radius, is going to change height depending on what the square root of x is at that point. So that's going to have x dependence in it. I like it. You guys love this. So this one doesn't look too bad, right? Try to set up what the integral will look like for this one, and then we're actually going to do this with shells too, just because. It's almost better to think of it like this, because then you just, how do you always get the radius? You start at where you're revolving around and you go out. For washers and discs, it's until you hit a wall. For shells, it's until you get to a representative rectangle. And the height, you can for shells, you draw the rectangle and see how tall it is. For washers and discs, I mean, it only relates to the radius. I love it. Right? The radius kind of defined by the function. So what's this integral going to look like? It's going to be pi. Integral from what to what? And what's a d what? Dx. Got to be dx. This is the washers one. So what's x doing? Going from
0 to 4.
0 to 4. So I really want you to understand. I don't care. Take that away. If I rotate around y equals 2, y equals 7, y equals whatever, that has no effect on these limits. These limits just say my region, what is that variable doing? I don't care what you're going to do next or how you're going to rotate it or where you're going to rotate it around. Who cares? And then inside here it's going to go. This is beautiful. This is too nice. Square root of x squared, so that's just x minus 2 squared. Ooh, the other way around, Jeff. Outer radius first, 2 squared, minus inner radius squared, x. It's a really good reason why you label those bad boys. And then this is, just go ahead and finish that out. And then we'll look at shells. And we have to get the same answer, or else one of the two methods has to be thrown out. I have to write to the Mathematical Society and say what the shit is. Probably not going to happen. troubles. Oh, you're way over there. Jeez.